All right, welcome. After last video's little detour into some predicate logic, I want to jump us back into the analysis of these algorithms that we've been looking at and introduce another tool, another mathematical formalism called asymptotic notation, better known by its nickname, Big O notation. So to just motivate us on why we want to take a look at this, I want to remind us of the three functions that we came up with for our three algorithms, 4n plus 1, 4n plus 5, and 4n plus 7. And again, let me just express what this means is that if our input size was n, then I think it was our minimum algorithm was going to take 4n plus 1 operations in the worst case. And again, for an input size of n, maybe it was, I think, our sequential search algorithm, might take a different number of operations expressed by this function, 4n plus 5, and so on. The last one, I believe, was for our string equals algorithm. So if these express the number of operations, these functions express the number of operations for those particular algorithms, then how can we maybe compare them to one another? Now, straightforwardly, we can take a look at each one and we can maybe plot their numbers here or plot them on a graph if we like. And straightforwardly with these three functions, sorry, we can see that one is greater than the other is greater than the other. That's fairly straightforward. In all cases, here 4n plus 1 will be less than 4n plus 5, and so on, at least for the cases that we're concerned with for values of n. At least for these functions, it makes it comparing them somewhat straightforward, but that's not going to be true for all functions in a particular class that we might want to compare. For instance, changing some of these pluses to minuses might mess things up for us. Or maybe changing the 4 out front to something different might also change things. Now we might say, well, are we changing the function too much in those cases? Well, maybe we are. But what we can see here, at least for these three functions, at least when we look at them in this table, we can see that early on for small values of n, like 0, the differences between these functions are actually quite great. So the difference between 1 and 5 is considerable, right? 500%. However, when we start scaling up, moving our n higher and higher, the differences, as we can see in these last three columns in particular, the difference between them starts getting smaller and smaller. The absolute difference between them remains the same. It's 4 here, 4 here, it's still 4 here, or 2 on the next column, next row. But the relative difference, how much that 4 matters to the whole, gets smaller and smaller as n grows bigger, which kind of makes sense, right? As n gets larger, then this fixed value, this fixed difference will get smaller and smaller as a relative proportion. We could say here the 4 is about 1/1000th of the whole, which is very small compared to the 4 here being considerable, like 80% of this one here. So the point that this table, that I'm trying to make with this table, is that these lower order terms, these smaller ones, seem to make less difference as the n gets larger and the higher order terms start to become very dominant. Okay, and of course here I've gone to 1,000, but this point could be made, more and more if we go up to 1,000,000 or 1,000,000,000 and start seeing that 4 becomes very negligible against maybe a size of n versus 1,000,000,000. Maybe 4,000 starts becoming negligible, or even 4,000,000 starts becoming negligible bonus, meaning that even though these numbers are relatively small, any additive constant that we add on the end here, we can find some n that's large enough that makes that constant seem very, very small. Okay. So what's the goal here? Why do we want to lump these functions together or group them together and say they're sort of the same when we can see clearly with this amount of detail that they are indeed different? Well, the reason is we want to focus on specifically what we're going to call their growth rate, how fast they grow. And these lower order terms usually don't make a big difference there. What usually matters is only the dominant term, the highest order term. And we sort of want to focus in on that term and use that as a representative of the growth rate. And again, here, all of these functions actually grow at the exact same rate. The growth rate is determined by this 4n, not by this extra plus 1, plus 5, plus 7. This actually just determines the starting value. We start at 1, or at 5, or at 7, and then what? Then we grow by 4 every time, by 4, by 4, by 4, by 4, by 4, by 4, and indeed we see that for all of them. So the growth rate is what we want to focus on, so we're going to use this new tool, which we're going to call asymptotic notation, or big O notation, and I'm going to define that right here. So asymptotic notation is sort of the mathematical jargon name, asymptotic. I might talk about that in a second. We more commonly call it just big O notation after the big O that we use in the notation. And the purpose of it, again, is to group similar runtime functions together. So let's start with a couple runtime functions. Here I'm going to call them f of n and g of n. Okay. Now I say here let's start with some runtime functions. What do I mean by runtime function? Well, remember in an earlier video I mentioned that not any old mathematical function is a good representative of the runtime of an algorithm, and that's because runtimes have certain assumptions, numerical assumptions about them, that we can bring to bear on the functions that express them. And what do I mean by that? Well, first of all, remember that our functions, that the runtime for a particular algorithm is usually a positive value, although we might include 0, meaning that we exclude negative runtimes. That doesn't make sense to us. And again, also we want to exclude functions where usually the normal observation is that the runtime of an algorithm will increase as the input size increases. And so we want to restrict ourselves to functions that sort of behave in that way. What that means is runtime functions typically have two properties. They are positive, or technically non-negative because we allow zeros, and they are increasing, or again, technically non-decreasing because we allow constant functions. But those two properties, positive, increasing, or non-negative and non-decreasing, are what we usually typically assume are true of our functions f of n and g of n, at least on the positive values of n, or at least on large values of n that we care about. So now let's say, okay, we've got two runtime functions like it says here. We've picked two out, f of n and g of n. Now, what we're trying to define here with my definition is that what does it mean to say f of n is in big O of g of n, or f of n is big O of g of n, or f of n is an element of the set big O of g of n. There's lots of ways we can phrase that, but often the sort of simple way is to say f of n is big O of g of n. Now, what we're trying to do is define this. So let's think, well, what functions f of n and g of n might be useful for us here? Well, on our previous slide we had a few candidate functions for f of n. I'm going to pick the first one, at least for my example here. Imagine f of n here is 4n plus 1. Then g of n, we could pick one of the other functions, and it would actually be true if we tried to prove this. But instead, I'm actually going to, usually inside our big O, we want to pick a simple function. 4n plus 1 is fairly simple, but it's not as simple as n alone, just 1n plus nothing, right? That function is fairly simple, and it's actually representative of all the functions that grow with the growth rate of what we will call linear functions, or functions with highest degree of their polynomial, if they're a polynomial, of degree 1. Okay, and so our three functions, 4n plus 1, 4n plus 5, and 4n plus 7 are all linear functions that have highest degree 1. So let's go ahead and assume, if we want to here, that what we're maybe trying to prove, and we'll do this in a second formally, that 4n plus 1 is in big O of n. Okay, but if we're trying to prove that, then what do we need to prove? Well, that's what's going to be set out here by my definition. Okay, and we're going to try here now to prove or not sorry, prove, to understand what this definition is asking us to prove if we want to prove something is in big O of something else, if f of n is in big O of g of n. And so what are we being asked to prove is everything I've got stated here in blue. Now, we're going to take a second here to sort of parse this out, because this is a logical and mathematical statement that has a lot of technical details in it, that if we just sort of overlook them, it's possible to misunderstand it. And so what I'm going to do here is I'm going to try and read out this, and as we go, try and translate it in our mind into the logical structure that this statement has. So let's start out here. It says here, there exists. Okay, that's why we brought in the quantifiers in the last video, the logical quantifiers of the universal and existential, or the for all and there exists quantifiers, because this statement now is technical enough that we need them to state what to formalize it in logic. Okay, so we need that existential to formalize this part of the statement, saying there exists. Well, what does there exist? It says here there exists positive constants b and n naught. Okay, so we might be able to cash that out a little bit. The positive bit is just saying b is bigger than 0 and n is bigger than 0. Okay, and they are constants. Okay, what that means is that they're not going to change, or they're not a variable like n. Okay, so even though this is n naught, this is a constant. Okay, it doesn't change with n. And then such that what? Well, such that for all of the n's greater than n naught, so again, n is a variable. It's not a constant, so it does vary. But we're saying we only care about the ones that are greater than n naught. Okay, interesting. So let's back up for a second again. Here we have a there exists something. Next we have a for all something. Okay, so it looks like we have an exist quantifier, a for all quantifier. This one's saying something about what values of n we are concerned with. And then finally we have it is the case that. Then we finally have just a mathematical statement, and this is sort of what our rule of thumb can be, or what we can take away on our scratch notes, which is f of n is less than or equal to g of n. Oh, I skipped over the b, because the sort of rule of thumb, if I blur my eyes, when I say f of n is in big O of g of n, I want to say f of n is less than or equal to g of n. But luckily in our definition here, there's a little bit more there. We actually need this constant b of n. We're not saying that they're strictly less than g of n. F of n is strictly less than g of n. We're saying it's less than g of n if we give g of n a little boost. We're allowed to multiply g of n by some constant b. Okay, maybe make it bigger. And since it's a constant, all we said was it's positive. B could be pretty big. Okay, it could be a million, could be a billion, could be a trillion, but it can't be n. And that's the important thing here, because it's a constant. Okay, so we can pick whatever b we want, but whatever b we want, it has to be fixed. It has to work for any n. It can't depend on n. Okay, so again, let's go through that. Let's see if we can now put these pieces together and make this a little bit more logical. Okay, so I'm going to pull out that predicate logic from last time. What do we have here? We've got f of n is an element of g of n. That's what, or sorry, big O of g of n. That's what we're trying to define. That's defined by an if and only if statement. That's this bit here. And then the rest of this is supposed to capture the definition. So let's see here. It says, what are we reading out here? It says there exists a b greater than 0. So that's our positive constant b. There exists an n naught greater than 0. That's our positive constant n naught. Okay, there exists, such that for all n greater than n naught, okay, such for all n greater than or n naught. It is the case that, that's what this little colon is saying, after all of these quantifiers, the colon is going to give us another proposition, probably a proposition with these variables in it, n, b, and n naught. Well, we didn't actually have n naught here. So we actually have f of n is less than or equal to, we're just pulling this down here, b times g of n. Okay, for which values of n? for the ones greater than, greater than n naught. And for what value of b? Well, whichever one we picked out here, okay? So I'm just going to simplify this one little bit more, and then we're going to try and, again, we sort of pulled all the pieces apart. Let's put them back together and see if we can assemble them and understand what they mean, okay? So the last bit, all I've done to simplify here is I've just compressed my two exists. So remember back in the last video, if we have nested quantifiers like this, if they're of the same kind, if they're both existential or they're both universal, we can just lump them together. So this is just a shorthand, makes it easier to read, and it really reads sort of like the English statement up here, where I've got there exist positive constants, sort of pluralized it, lumped it together, saying they're both positive, one's named b and one name's n naught. Okay, so now let's take this little logical statement and see what it's actually saying for us. And there's maybe a couple ways we could go for it, but I may want to start here because this part is the most meaningful to me. This part I already understand. F of n is less than or equal to b times g of n. Okay, now remember, let's just, sometimes it's useful for an example here. So let's go back to what our example was. We said, well, what if f of n was 4n plus 1 and g of n was n? Well, if we didn't have the b in there, 4n plus 1 is less than or equal to n. That's never true because of the 4 out there, right? The 4 out in front. But the 4n plus 1 might be less than or equal to something times n. What should we multiply n by? I don't know. We'll look at that in a second because I'm going to prove that in a second. But the idea here is that giving us that little wiggle room is this constant b. Okay, we get to pick b. Now, why do I say that? We get to pick b. Well, this logical statement here says there exists some b that satisfies this condition. It didn't say for every b this condition holds, or for a specific b equals 10 it holds. It says there is some b that this is true for. Now what that means is if we're trying to prove this statement true, when you're trying to prove an existential statement true, all you have to show, if you're just trying to show that something exists, if all you have to do is show one example of it. One example, any example, meaning this is where I say we get to pick b. We get to pick b. Any b that works is good enough. And so we get to pick it. And so what that means is when you're using this definition for your own proofs, you might pick a different b than I do. And that's fine, because my b might work and your b might work, and any b that works is fine. Okay, so pick the one that you like, if you like. Okay. And that goes for our n naught too. We get to pick that one too. Now, let's factor that in. Why n naught? It's playing a slightly more subtle role here. What is this business about n naught? Well, first of all, n naught is some number bigger than 0. It's positive. And we're saying that this condition only has to hold for all of the n's larger than n naught. Okay, well, what candidates are there for this n0 or n naught? Well, a good candidate for n naught, the one that I usually will pick if I don't have any better one to pick, would just be 0 itself. That would be all the positive numbers. If I can show this is true for all the positive numbers, then I'm done. I'm happy. Okay, I've proven my big O bound. But if that doesn't work, for some reason, for some of our functions that are not well behaved, they might, this less than or equal to might not be true for any b we pick unless we change the cutoff point from 0 to some other positive number, maybe 10. Maybe the relationship works after 10, n equals 10, or maybe it works after n equals 100 or 1,000,000 or 1,000,000,000. It doesn't matter. If you can find some cutoff point, because again, this is one of the ones we get to pick. If we can find any cutoff point after which this relationship holds, after which it has to hold all the way to infinity though, okay, all of the n's after, there's infinity of them, but if it holds after some cutoff point, then we're okay with, well, we don't care where that cutoff point is, okay? It just has to be positive. And even that condition can be relaxed usually, because if you could find a cutoff point that's negative, then 0 works too. And so that's kind of, the positivity part is just to make sense. What do you mean input size that are negative? Input sizes that are negative don't make sense, so we'll just, what's the point in thinking about them? So we're going to just leave them behind. Okay, so I think we've sort of looked at the different pieces, seeing what we're trying to prove. So let's sort of, again, take the bird's eye view of this. If we're trying to prove that f of n is in big O of g of n, we're trying to show that it's less than or equal to g of n, kind of, with a b in there. The b makes it easier on us because we don't have to show it's exactly less than or equal to g of n. We get to inflate g of n if we want to. That's great, okay? Meaning what? We get to pick that b. So if we can show that it's less than or equal to b times g of n, that's the bulk of the work there, 95% of the work most of the time. Then every once in a while we might have to change the cutoff point. Some functions are not well behaved. So we're really just trying to see if one function is less than or equal than the other. So let's go back to our example here. I guess I called them f of n, g of n, h of n on this slide, but as we consider them, I'm going to do it one at a time. And usually we'll just call them f of n. But these are our three functions. And each one of these is in big O of n. And so that's sort of what I want to start out with here is, let's see if we can do that. And I'm just going to say, let's do that on the whiteboard because that makes it a little bit easier. So let's start with our first one. We've got f of n is 4n plus 1. And what I'm going to try and prove here is that this is in big O of n. Why don't we go again back to our definition and try and see, well, what did that mean? Okay, I'm going to sort of put it together. I'm going to need that my 4n plus 1 needs to be less than or equal to, here my g of n is n, but we've got some b here. Okay, and really we need to show this for all n greater than n naught. So we also get to pick an n naught. Now in our scratch work, I really like to focus on the we get to pick these two bit. The reason I like to focus on that is because that becomes very important, is once we pick them, we're usually done. So once we've done enough of our scratch to find out what b is and what n naught is, we can put together the proof no problem. So we're done. So that's what I want to do here. And so let's think. Let's go ahead. And usually I start with b. Not everyone wants to start with b, but I do. I think most people do. So let's try and start with b. What's a good possible b we could pick here? Now I'm going to start out by saying, someone might come by and say, well, what about b equals 4? I want to say, okay, hopefully we can see that that's not going to work because we're never going to get that 4n plus 1 is less than or equal to 4n. Why? Because of this, the plus 1 on there. The plus 1 makes it bigger, right? So the 4n here is actually technically less than. And so this is never going to work out for us, all right, because this plus 1 makes it bigger. So that means our candidate of b equals 4 doesn't work. So I might go back and I might say, well, tell me what b do you think is going to work? And there's lots of candidates that work. But I think a lot of us might say, well, the next kind of obvious candidate might be b equals 5. Okay. And some of us might have other options here too. Okay. And if you pick b equals 10, guess what? That one works too. So good on you. Okay, try and see when it works. Okay, well, what are we going to do here? I'm going to say, okay, now I'm trying to prove 4n plus 1. I want to say it's less than or equal to 5n. Now, is this true or not? Now, some of us, our mathematical instinct and intuition might be going, well, yeah. Okay, well, yeah, that's true. But it's not always going to be true. And maybe I'm going to try and make that obvious for us. Let's pick a value of n. Okay, I've got my 4n plus 1. I've got my 5n here. If I pick a value of n, I'm going to pick 0. If I plug it in, 4n plus 1 gives me 1, but 5n gives me 0. This is not less than or equal to in the way that we expect. But when we get to 1, let's check here. 4 times 1, that's 5. 5, in this case, we got an equal to. Let's keep going, just, test the waters here. 2, we get 8 plus 1 is 9, and 10. Now we got less than. Okay, let's just do one more. I think we know where we're going, right? But we do one more time. We're going to get 3n plus 1 is, well, 3n is 12. That gives us 13, right? And this looks like 15. Looks like we're less than again. And let's just go in and pinpoint a couple pieces here, okay? In this case, I want to consider this, I want to compare this 4n plus 1 here and consider a slightly different function, 4n plus n. See how these two functions relate. Okay, why did I write 4n plus n? Notice that's 5n. Okay, so why do I want to say that? Well, when we were at 0, our n was less than our 1. And because of that, the top function here was less than the bottom, meaning 5n was less. And that's what we got here. I put an x, but this was, oops, I put it the wrong way now. And now I'm just messing myself up. But this was strictly greater than when what we meant was less, what we were looking for was less than or equal to. So this was a violation. This one was wrong. But when n became 1, these two functions are actually the same function. And we saw we got equals. And then, as our n gets bigger than 1, 2, or 3, now it becomes bigger than this value here. So well, basically our over approximation, our 5n now, keeps getting bigger and bigger, leaving behind the actual function we were looking at, 4n plus 1. But since we were just looking for something that was less than or equal to, we can see that indeed, that for these values of n, and actually for all that come after, our relationship is indeed satisfied here. So we might say that this is true for all n. We could say here, there's two ways to say this, greater than or equal to 1, which is fine. If you leave it like that, I'm perfectly happy with that. But the way I wrote the definition, we technically had a greater than symbol here. So you could also write for all n greater than 1, or for all n greater than 0. It doesn't have to be true for 0, it just has to be true for the ones greater than that. And so these statements all are effective at proving the big O bound that we were looking for here. So they're all equally effective, whichever one you land on is just as good. Okay, but that last little bit was sort of focusing on, well, what values of n naught would this be true for? Okay, so I kind of want to put that together, or put those pieces together into one sort of final little observation here. I'm basically saying 4n plus 1 is less than or equal to, we kind of just guessed at 5 here and tried to make it work, but the trick that I'm using here is I'm actually promoting 1 here to n. So I'm going to say 4n plus n, which we know is equal to 5n, right? So by promoting the 1 to an n, it should be fairly straightforward. That's only going to work if n is greater than or equal to 1. This function will only be greater than or equal to this function if, well, let's cancel this out and cancel this out, if n is greater than or equal to 1. Well, that's what I wrote there. Okay, so that was again giving us this final condition that we're looking for. All right, so this is my our first example that I've also got up here on the slide. So why don't we just take a look at sort of, now that I did the scratch, how do we put that together? So first of all, for these proofs, usually, for your purposes, if you're not trying to prove this to, your teacher or your boss or something, then you don't really need a formal proof. You just need the scratch. Once you've done the scratch, you walk away and you're done. But if you do need to prove it, for an exam or your boss or an interview or something, here's how you might do it. So here, I first usually just say, well, what do I need to prove? And what do I need to prove just means go look at the definition that we just went over and see what it says. So in this case, what do I need to prove? I need to find these constants. Here I'm saying I need to find them because I get to pick them. But if I can find some constants b and n naught, such that for all of the values of n greater than n naught, it's true that 4n plus 1 is less than or equal to bn, then I'm done. That's what the definition tells me I need to prove. Now here, all I've really done is taken the definition and plugged in what my f of n is and what my g of n is. So I plug them in, and that usually just tells me the algebra bit that I need to be focused on. This 4n plus 1 is less than or equal to bn. Okay, now what? Well, now I need to show what these are and show that they work. Now on my scratch, I already did it. Okay, but now I want to take the relevant pieces from my scratch and piece it together into my proof. Okay, so first of all, this seemed like it was an important part of my argument. Notice that 4n plus 1 is less than or equal to 4n plus n whenever n is greater than or equal to 1. That was the important argument on all that scratch that we had that made the important, that's what I sometimes call the heavy lifting of the proof. Okay, this fact was the critical one. If it wasn't true, the rest of it breaks down. Okay, so we bring this one in, and on top of which this one told us that condition on n when we could be confident. So that means our 4n plus 1 must be less than or equal to this side, which is 5n, for all n greater than 0. And here I've just translated this statement into one that better matches my definition, so it's clear that we see it. Okay, and again, this is a fairly simple example. All right, this one is not exactly the most challenging of them. In fact, that's why we're starting with it, is because we didn't need to use any fancy mathematical tricks to get the proof. Right, let's consider another one then. Let's see if we can change that idea. We'll do a little more scratch or try it again with our function 4n plus 5. Now, as I've sort of been hinting, this is also a linear function, okay, meaning that we should also expect it has this order n. Sometimes big O n, another way of saying big O n is order n. So we hear people say that order n squared, order 2 to the n. They're just another way of saying big O of n. And so you might hear people say that. I'm trying not to confuse you here, but as you saw, I just sort of lapsed into that way of speaking too. But here we're trying to show that this 4n plus 5 is in big O of n. We're going to use probably the same technique as before. But let's just see what we can do here. Let's say 4n plus 5. We said here, in the last time I said, well, is this less than or equal to 4n plus n? Can we do the same trick? Does it work again? It does, except what we'll notice again, if we cancel out these two, I'm not going to actually scribble on it this time, but if we cancel them out, we end up with the condition n must be greater than or equal to 5. Okay, what that means is in this condition, our b that we get from this function here will still be 5, 4 plus 1, but now the n naught that we have, well, if it works for all of the ones greater than or equal to 5, then this one will work. We can pick an n naught of 4. Remember, we only need to work for the n's greater than n naught. Okay. So what that means is, again, I've just done a little scratch, and I've come up with a b and an n naught that I think works. If all you were concerned with was verifying this relationship, then you're done. Okay. However, if you have, if you need to convince someone, you might want to take this scratch work and put it into a proof. So let's look at another one, because our other function is also very simple, and so why not do them together here? The thing I want to introduce here is that there's more than one technique we can use, and since these functions are fairly simple, the same technique will work. Again, if we try the same one again, 4n plus 7 is less than or equal to 4n plus n, using that same approximation, we could just say now that, 7 must be less than or equal to n, or n must be greater than or equal to 7. So again, we could use the same technique. What we're noticing here is just that this crossover point, the point where one function becomes greater than the other, is just moving to the right as n gets larger, right? In our first example, it worked for n at n equals 1. Now, at our second example, it's n equals 5, and then, or 4, depending on how you write it. And then same thing in our last example, it's n equals 7. But let's look at a different way. Sometimes this technique isn't going to work for us. I might give you a better example in a second. But for the moment, let's just look at another approximation method we can use. So again, we've got this 4n plus 7. Now, when I say this here, another approximation method we can use, what I'm trying to say is that in approximations, which is what we're dealing with in this definition, the less than or equal to means we're dealing with an approximation instead of an equation. An equation is something that has equality in it, okay? And most of our algebra, most of our math is focused on equations. And every once in a while we would sidestep into inequalities. Well, now inequalities and approximations are going to become very important. Now what that means is all the techniques we use in algebra, since they're focused on equations, they're focused on the types of manipulations that derive from the equals operator. But we are going to be approximating, are going to use any tools we can use that work with the less than or equals to operator. Now the first one is all the ones that work with equals work with less than equals. That means all our normal algebra, good to go. You can use that, okay? But with approximations, within inequalities, there are other tools, there are other ways we can go. And here's the sort of the good news, I guess. We got good news and bad news here. The good news is almost anything you can think of is going to work. Okay, 4n plus 7 is less than a billion n. Guess what? That's probably true. Okay, but identifying when a tool works or when it won't work is kind of the important extra bit you need to add in approximations, and that maybe is the bad news. Okay, the good news is almost any tool will work in the sense that you can use it, but the bad news is it might not get you the result that you're looking for. And so you spend a lot of time looking for the right tool for the job. And so that's why I want to introduce here now another tool. The tool that we've just been doing so far is just saying, take that lower order term and just replace it with one upper order term, if you will, okay, higher order term. Here what I'm going to do is another, this is sort of more a substitution or replacement rule. This one I'm going to call a promotion rule. Okay, this lower order term, it's a problem because it's not of the same order as our higher order term. So we use one technique up above, we just replaced it. In this one I'm going to say promote it. Leave the same scalar out front, but promote the term, the variable part of the term, to the same degree or the same whatever function it might be in our higher order term. Okay, so in this case, since my higher order term was n to the power 1, I chose to promote this to n to the power 1, and this gives me 11n. Okay, now, what does that change for me? This has changed my b. Using this technique over here, we have b equals 5, and n not equal, well, if n is 7, greater than or equal to 7, we could choose 6. Okay, but here, in this case, our b now is 11. This different technique gave us a different constant b, but it still works. And in fact, this one works for all n greater than or equal to 0. Actually, we could actually make it 0. Now let's see, how do we know that that's true? Well, what did I actually do to this term here when I promoted it? I multiplied it by n. Okay, now I guess, when does multiplying by n make this term bigger? When does it make it bigger? Okay, well, if n is a number that is bigger than 1, it will make it bigger. If it was equal to 1, then it's the exact same size, so that's fair too. But if it was less than 1, if the n here was less than 1, we made this term smaller. Okay, so I actually picked here n 0, but I need to be very careful. Why does n not equal 0 work here? All the numbers between 0 and 1 actually wouldn't work. But remember, our rule is saying it's supposed to work for all of the n's, that are greater than n naught. So that does not include 0. But then also, we usually assume n is an integer. So the next available n that's greater than n naught is 1. And that one it does work for. Okay. So this promotion rule usually works for n greater than or equal to 1. It depends what you're promoting to. Okay, so you need to be careful. But it's clearly for promoting to a linear term like this, promoting it to n to the power 1, usually will work for all n greater than or equal to 1. So in that sense, it can be a more powerful tool in your approximation toolkit than just replacing the term altogether with a higher order term. Just because when I say it's more powerful, I mean it works for more values of n. Okay, and some will think that that means it's more powerful. Okay, let's go back and take a look at our two other proofs here and see how we put that together, the pieces together. Again, we're going to have very similar proofs, so I'm not going to go over all the bits. But the next bit here, the next piece here, okay, the next function is going to be the same. What we need to prove is the same. I've only changed my 1 to a 5 here. Okay, but actually in this proof I opted to use the exact same technique and highlight that it only changes our n naught. So I chose n greater than 4 here. Okay, and so our next example, which was 4n plus 7, we have, I chose to use this different technique. So again, what we need to prove is exactly the same, but what I chose to prove as the technique I chose to prove here is use the promotion technique. So here, I just replaced it. Here I decided to promote it. So this is true whenever n is greater than or equal to 1. So I chose again my n, I chose my n naught here to be 0. Yeah, for all n greater than n naught. So here we have, again, we could have done a different proof if we wanted for 7n, for all n greater than 7, not 7n, 5n, for all n greater than or equal to 7. But we've chosen here to use the promotion technique, which is just another tool in our toolkit for dealing with upper bounds or approximations like we're looking at here. Okay, let's continue and look at one sort of final example or set of examples here, which are again going to be some functions that are actually in big O of n squared instead of n. So this is just going to be a different set, and it's just going to be a little bit extra practice to work with. So let's try and do that. So let's start with our first example here. F of n is, what do we have here? 7n squared minus 2n plus 4. Okay, and again, usually a good rule of thumb when we're working with asymptotic notation is find the higher order term, because if we weren't told ahead of time what we were trying to prove here, a good guess would be n squared, because this is a quadratic polynomial and the highest degree is 2. Okay, so if we're trying to prove that, then again we might just sort of quickly on our scratch write down the relationship that we need to prove, which that this is less than or equal to b, and now it's times n squared for some n squared, some b multiplied by this extra function n squared. Now, what value of b do we think might work here? Okay, now here, and again I want to maybe make a couple of recommendations. There's a couple ways that you can come at this. guessing is an okay way, and I think a lot of us, I guess I should mention that when we're doing approximation, unlike equations, guessing what the right answer is on an equation is an okay method. It's just really hard. Okay, if you don't know what the answer is, just guessing out of the blue what one of the infinite numbers is going to be the right answer is really hard. Okay, but in approximation, there are infinite numbers of b here that might work. So just guessing one that works and trying to see if it works might be a good way to go. And so I'm actually going to use an instinct. I'm not sure if this works, but it's an instinct that I've noticed a lot of my students might use here. So I think I'm just going to guess 7n squared. Let's try it. When I say try it, what I mean is just pick some numbers and plug them in and see what they are equal to. So I'm going to do my 7n squared minus 2n plus 4. I want this to be less than or equal to 7n squared. And so I'm gonna plug that in, and I'm going to see what values does it work for. Okay, what values does it work for? So let's go. 7 times 0 squared is 0. I'm maybe going to write this one out. 0 minus 0 plus 4 equals, well, 4. Okay, and this one's just going to be 0. So unfortunately, we get the wrong relationship here. So I'm going to mark that as fail. Okay, so maybe my guess of 7 is wrong, but let's keep going. Let's plug in our 1 now. What do we get here? We get 7 minus 2 plus 4 again equals 9. And this one will get 7. Looks like again. Okay, I don't go down that easy. I'm not going to give up. So I'm going to try one more. Now if this one fails, I give up because I don't want to keep trying them all day. Maybe my guess is wrong. Or if this one succeeds, maybe I've caught on to something. So maybe I'm happy. So let's check it out. Okay. So the next one, this one, now we need to do actual math, right? 2 squared is 4. 4 times 7, 28. Minus 4 plus 4, those cancel out. So that just gives me 28. And this is 28 over here, so it looks like we got an equal, so we're actually there. All right. Now, I think it might work after 2, but usually if I'm just guessing and trying, how do I know? Maybe 2 is magical. It works for 2 and none of the other ones. So I'm going to at least try 3 and see if 3 works. If 3 works, then I'm pretty sure. Or go jump on and plot it. If you plot it, it might work too. Okay, you might be able to do that if you happen to have an easy plotter nearby. I don't have one right here. So let's try here again. 3 squared, this is getting a little bit harder. 3 squared is 9. 9 times 7 is 63. Okay, minus 3 times, that's 6, plus 4. So that's actually going to give us a minus. The minus part is now dominating the plus part. That's good to see. So we actually get, what, minus 2 here, so we got 61. And then up here, oh, we did that 7n squared bit already, which was 63. So we now actually are going in the right direction, so we're good. So we could just, if again, all we wanted to do was convince ourselves that this worked, we might just guess here, and then we're done. The proof for this is a little bit harder. Not really, not super hard, but it's going down a different path than the one we did before. The proof for this, so let's see if I can break this out and try and do a little bit of the proof now. I'm not going to do the whole proof here because I'm just showing another tool and how the tool works. Okay. If what we're trying to prove here that 7n squared minus 2n plus 4 is less than or equal to 7n squared, doing a little bit of algebra now, we could just minus 7n squared on each side, which would leave us with minus 2n plus 4 must be less than or equal to 0. Now I want to pause here in the algebra to see, well, what is this saying? That's saying that we're trying to argue that this pair of terms, this extra chunk of the formula, is less than 0, meaning is negative. Okay? If we're trying to assert the first line here, we're asserting the second line, which means that these extra terms turns out to be negative. Now, what we did in this table over here, finding x's and checks, was trying to find out when was this term negative. And a little bit of extra algebra does that for us here too. I'm just going to move the 2n to the other side and then finish off our algebra. And it tells us n must be greater than or equal to 2. Well, that's what we just found here too. Okay, so that's the extra bit that I might include in my proof. I might say this line is less than the right-hand side here because this part is negative whenever n is greater than or equal to 2. So piece that together in your own proof. We've got a slightly different one here, okay, on the slide that I had. So see if you can take this work and put it together. Okay. Now let's tackle this one with another example or two. Okay. So I wanted to just say that just guessing worked, but what if you can't guess? What if you didn't know that was going to work? What could we do instead? Well, another tool we can do here is, and it kind of factored into that last example, is that negatives only make things smaller. This is a negative term. It only makes things smaller. So when we're doing the less than or equal to option here, when we're looking for an upper bound, something that's bigger, those things don't help us. We can just get rid of them. So this might have been one step on the way to where we were going before. It might not be the best step, but it's a step to somewhere else. That's where we're going right now, which is if 7n squared minus 2n plus 4 must be obviously less than or equal to 7n squared plus 4, all we did was drop out the negative thing, the thing that made it smaller. Okay, and if there was more than one term that was negative, we could lump them all together and drop them all out here. Again, what is the observation we're making here? Is we're saying that this is less than or equal to 0, as long as n is positive, which again is our operating assumption. So we're just saying that since this is less than 0, I'm replacing it now. I know this is true. I'm using this rule. I'm replacing it on the left-hand side. On the right-hand side with 0, I'm just dropping it out. Okay, we're done with that. Now what do we do with this? Well, this one's not as hard to work with. This one, we could use one of our other techniques. We could say this is less than or equal to 7n squared plus n squared. That's the substitution rule, where I'm substituting one for the other. Okay, well, this one only works then if n squared is greater than or equal to 4. N squared is greater than or equal to 4. Now that takes a little bit of extra work, but maybe not too much extra work to see that that works when n is greater than or equal to 2, just taking the square root of both sides here. So that was one tool we did here. This one I call substitution or replacement. I'm going to put here, or. That was one rule we could do, the substitution. What about promotion? We could do promotion too. 7n squared plus 4n squared. Here, I'm multiplying by n squared, so here we're assuming n squared is greater than or equal to 1. Remember that same rule we did last time, okay? So square rooting both sides here leads to the same conclusion. N must be greater than or equal to 1. Okay, but this rule here gives us a different n than we had here, and I call this one usually promotion. So I guess for this 7n squared minus 2n plus 4, I've sort of shown us 3 techniques we could use here that I've called substitution, promotion, and then the first one we can just call guess. And and I use that as my first one, but usually I use that as my last resort, not my first resort. Usually there's some technique that I know is going to work ahead of time, and then only if it doesn't work do I just guess. Okay, so when I say I know it's going to work, I hope it's going to work, maybe is a better way of saying that. And then if it doesn't work, I will just guess. Because guessing usually is trickier. You have to be more clever. Okay, let's try another one. I want to do g of n now. Okay, so g of n, again, we probably want to prove this one is in big O of n squared. So what techniques do we have? We can probably use those same tools, and maybe I'll leave it to you to practice some of the other ones. I just want to maybe tackle one. First of all, let's get rid of that minus. Okay, so here I might do n squared plus 4n minus 5 is less than or equal to, the minus 5 only makes it smaller, so obviously it's less than or equal to the n squared plus 4n alone without the minus 5. Right, okay, so we'll drop it out. What does that mean for us on the next step? Well, now I might say use replacement or substitution. And maybe I'll do both of them. Sorry, replacement or promotion. Maybe I'll do both of them. So the first one here, n squared plus, if I just want to replace this with another n squared term, that was one way we could do it, then that meant, on my scratch over here, n squared must be greater than or equal to 4n. Sorry, n squared must be greater than or equal to 4n. That means drop the n, drop an n here, n must be greater than or equal to 4. So this was an n greater than or equal to 4 move. Okay. Again, I might write or, because we're going from this line here, not this line. We could say that n squared, we'll do the promotion rule. Now the promotion rule here is saying promote the n to an n squared, giving us 4n squared. And again, that's by multiplying by n, meaning n must be greater than or equal to 1. See these two rules, they just work in different conditions on n. But most of the time, both of them will work for whatever you're doing, so pick the one you like. Okay, and this one here, I guess the first one here resulted in a b equals 2. The second one here resulted in a b equals 5. Again, all you need this for is to convince yourself. Once you get the scratch, you're done. If you do need to convince someone else, then maybe you want to take this scratch and package it in such a way that your reader, your audience, is going to be able to use it easily, like a proof. Let's just look at the last one, 3n plus 5. Now here, this is a little bit strange, and I'll mention why. Well, the big O term here usually means less than or equal to, but a lot of the time, when I say means this, I mean that less than or equal to that's factoring in here. We sometimes use this to build our intuition. But most of the time we use it when we actually mean equal to, which is sort of interesting. And I'll bring out more of that in the next video. But this is a case where we actually have a strict less than. Okay, 3n plus 5 strictly grows slower than n squared. But we can still show the big O relationship. So let's see if we can do that here. I think the one that's going to work the best here is, well, we could do replacement, but I want to do promotion. I think promotion is the one that feels natural to me. And that means promoting both of my terms. I'm going to promote the first one to n squared and the second one to n squared, which actually gives me 8n squared. But promotion again worked for any n greater than or equal to 1, so I might use that one here as well. Now that shows that it is strictly less than. Well, it doesn't actually show the strictly part of less than, but it did show the less than or equal to bit. And so we'll have to leave it to the next video to confirm that it is actually strictly less than. That 3n plus 5 is indeed in big O of n squared, but we can also show it is in big O of n. Okay, and the other two we can't. F of n and g of n we can't show are in big O of n. That's just impossible. All right, maybe I'll just finish by looking at sort of the formal version that I've got here on the slides. Again, the proof that I've got structured here is going to be set up the exact same way. Let's just look at the technique that I've used here. So at least in this first one, it looks like I used the technique where I drop out the 2 of n, the 2 times n, sorry, and then I promoted the 4 to n squared. So in this example proof, I dropped out the 2n and then promoted 4 to 4n squared. For our next proof, let's see what we do here on the slides again. It could be a different technique depending on how you solved for your b and your n naught. But it looks like here I dropped out the 5, and it looks like again a promotion technique was used. And what about our 3n plus 5? Well, I used promotion when we worked it out on the board, and it looks like indeed, yes, that was the technique I used here as well. So these are, again, just sort of formalizing the 3 proofs we did just informally with Scratch by trying to make them a little bit easier to digest for our reader. Okay, that's all I wanted to do in this video to introduce asymptotic notation. In my next video, I'm going to continue talking about asymptotic notation by introducing what we'll call big omega and big theta notation. And that just extends what we were looking at here, so it's going to give us a little more practice using these same techniques with approximation on these same functions, but using a slightly different perspective. So thanks a lot for watching, and then stay tuned, and we'll see you in that next video.